Hello and welcome to The Space Above Us, Episode 109, Space Shuttle Flight 38, STS-35. A little bit of the old Ultraviolet. Last time, we talked about the final fully classified Space Shuttle mission, STS-38. We engaged in a little more speculation than usual, but it was pretty well-informed speculation that at least made sense to me. And if nothing else, the story of Prowler is an interesting one. Today, instead of trying to unveil the secrets of Atlantis' payload bay, we'll be trying to unveil the secrets of stars and galaxies with STS-35. First though, it's time for another check-in with the Galileo spacecraft. Galileo, of course, is the Jupiter-bound space probe that we saw deployed on STS-34 back in October of 1989. Since then, it's made its way to Venus, where it swung by and picked up a little extra speed. Its next stop was Earth, where it would mooch off the gravity and momentum of the planet in order to give its orbit another little boost. We'll get to this in a minute, but STS-35 lifted off on December 2nd, 1990. 6 days later, with the mission still underway, Galileo returned to Earth, passing within 1,000 kilometers of its home planet. As it passed through the Earth-Moon system, it produced some gorgeous images of the two celestial bodies, and was the first spacecraft since Apollo 17 to image the far side of the Moon. We'll see Galileo again in October of 1991 when it makes a pit stop on its way to its next gravity boost. Jupiter is pretty far away, but not quite as far as the subject of today's mission. Stars, galaxies, quasars, and other stuff not exactly in the neighborhood. Packed into Columbia's payload bay were not one, not two, not three, but 4 specialized telescopes. Now you might be wondering, what makes these 4 telescopes so special that NASA is willing to expend considerable resources in order to fly them in the back of a shuttle? There's tons of telescopes on Earth, let's just use those. But there's a problem with telescopes on Earth. They're at the bottom of a soupy ocean of gas that we like to call the atmosphere. I'm sure that we're all big fans of the atmosphere, but it really messes with light coming from outer space, especially higher frequency light. Remember how everyone was pretty upset about the hole in the ozone layer? Well, for one thing, it's getting better, so keep up the good work. But the reason everyone was so upset is because ozone plays a key role in blocking ultraviolet light from the sun. Ultraviolet light is what you get if you go up the rainbow through blue, indigo, violet, and then keep going out of the visible light. Normally, blocking UV light is great. UV light is energetic enough to damage DNA and can cause all sorts of nasty effects like skin cancer. But in the case of astronomy, UV light carries all sorts of information that you can't get from visible light, so having it blocked is a real problem. The way that this was handled in the past, and still sometimes today, was that instruments would be flown on high-altitude balloons. These lasted for a fairly long time, but were still in the soup, even if they were above most of it, so some UV light was still being blocked. Another method is to use a sounding rocket. These are small rockets compared to orbital-class launch vehicles, but they're still pretty big. They basically pop out of the atmosphere for a few minutes, and then fall back down without entering orbit. Such a flight might provide you with around 5 minutes of observation time, 300 seconds. By putting the scientific equipment in the back of a shuttle, you could get well over 300,000 seconds of observation time. Big difference. All this gear would be fitted onto unpressurized Space Lab pallets in the back of Columbia, making this our 5th Space Lab mission, but only the 2nd unpressurized one. It's been a while since we've seen a Space Lab mission, so let's do a quick refresher. Space Lab is a system of modular elements that allows for flexible science missions based out of the Space Shuttle payload bay. Sometimes these are pressurized modules, which sort of resemble a section of the ISS. Astronauts would float down a long tunnel into the payload bay and perform experiments in the module. But there's also support for unpressurized modules that are controlled from the flight deck, which is the case here. For those keeping track at home, the last time we saw a Space Lab mission was STS-61A back in October of 1985. You can learn more about that in episode 89 of the podcast and enjoy my failed attempts to pronounce German words. Commanding this mission is the last person to fly in both the Space Shuttle and Apollo command module, Vance Brand. We first met Brand back when he almost had to fly a mission to rescue Skylab 3, but his first actual flight was the Apollo-Soyuz test project. Since then, he flew the first operational shuttle mission, STS-5, the MMU testing flight of STS-41B, and now we're seeing him one last time on STS-35. This is his 4th and final flight. Joining Brand up front as pilot was Guy Gardner. We've seen Gardner before as well, flying as pilot on the classified flight of STS-27. For some reason, I thought Gardner was around for longer, because I was surprised to learn that this is his second and final flight. Moving back on the flight deck, we find Mission Specialist 1, Jeffrey Hoffman. We saw Hoffman on STS-51D, which deployed the ill-fated SYNCOM 4-3. When the spacecraft failed to activate, Hoffman and David Griggs performed the first contingency EVA of the Shuttle era, in order to attach the improvised fly swatter device to the end of the Shuttle's robot arm. This is Hoffman's second of 5 flights. Alongside Hoffman was Mission Specialist 2, Mike Lounge. Lounge's first flight was on STS-51I, which chased down and rescued the stricken SYNCOM 4-3 that Hoffman and his crew were forced to abandon. Last time we saw him was on STS-26, the return to flight mission, where I forgot that though his first name is John, he goes by his middle name, Mike. Whoops. Also, Lounge holds the dubious distinction of maybe being the only person to launch into orbit without wearing their seat restraints. See episode 87 for details. This is Lounge's third and final flight, so please buckle up this time, Mike. And moving down to the middeck, we find Mission Specialist 3, Bob Parker. We last saw Parker flying all the way back on STS-9, John Young's last mission. That makes sense, since STS-9 was also a Space Lab flight. It also makes sense given that Parker has a PhD in astronomy, and we've got a bucket of telescopes on this flight. This is Parker's second and final mission, but I thought it worth mentioning that he had quite a run at NASA. He joined as a scientist astronaut in 1967, serving in various roles including Capcom on Apollo 17, flew in 1983, again on this flight in 1990, and then moved on to other roles within NASA, finally retiring in 2005. Wow, all veteran crew, huh? Actually, no. For the first time since 1986, a shuttle is flying with Payload Specialists again. Just to remind you, astronauts fall into 3 categories. There are pilots, who fly the vehicle and keep its systems happy. This is obviously the pilot and commander. Then there are mission specialists, who focus on stuff like deploying payloads, operating the robot arm, running experiments, or performing spacewalks. Both of these categories are career astronauts, where this is their actual job. They are employed by NASA or sometimes other space agencies. The third category is Payload Specialist. A sort of reductive way of thinking of a payload specialist is as a guest astronaut. This isn't their main job, and they'll usually only fly once or twice. But they have some expertise that justifies them flying alongside some payload or experiment. Likely the most well-known payload specialist was Krista McAuliffe, who perished on STS-51L. The concept of a payload specialist was never super popular in the astronaut corps, with a common sentiment being that those roles could be performed by mission specialists. But sometimes you can't beat having an expert on site to troubleshoot a tricky experiment. And while astronauts are dedicated and driven people, you'll never beat the dedication and drive of a person who spent the last 10 years of their lives working on their experiment. Anyway, this is all a long-winded way of saying that payload specialists are back, so let's meet the 2 that will be flying on STS-35. Payload Specialist 1 was Sam Durrance. Samuel Durrance was born on September 17, 1943 in Tallahassee, Florida. Durrance earned a bachelor's and master's in physics and a PhD in astrogeophysics. At the time of this flight, he was the principal research scientist at the Johns Hopkins Department of Physics and Astronomy. He finds himself on this flight because he's the co-investigator for the Hopkins Ultraviolet telescope currently packed away in Columbia's payload bay. This flight of Astro 1 is his first, and he'll be back one more time for Astro 2. And rounding out the crew was Payload Specialist 2, Ron Parise. Ronald Parise was born on May 24, 1951 in Warren, Ohio. Given the nature of this flight and the CV of our other payload specialist, it probably will not surprise you to learn that Parise earned a bachelor's in physics and a master's and PhD in astronomy. Parise is flying since he helped create the Ultraviolet Imaging Telescope, but he's actually supported a bunch of missions, both human spaceflight stuff at Johnson and astronomy-focused stuff at Goddard. This is his first flight, and like Durrance, he'll be back for Astro 2. I've already mentioned in previous episodes that this mission had to be rescheduled a bit. Delays in any space program are a bummer, but hey, they happen. No big deal, right? The crew sits tight for a few more weeks and then it's pressed to MECO. The experience for this crew was a little different. Buckle up because this is kind of ridiculous. The Astro 1 payload was originally supposed to fly in March of 1986. It was actually the next flight after STS-51L. After the accident, the shuttle fleet was grounded and the mission was postponed. Over the ensuing years, a few changes were made. Several of the crew members either moved to other missions or retired from NASA. In 1987, a star exploded, or rather light from its explosion reached us, and in response, an X-ray telescope that was going to fly later was added to this mission, joining the 3 ultraviolet telescopes already on board. Eventually, the launch was scheduled for May 9, 1990. This had to be delayed due to some issues with the payload and some problems with the oxygen system and a coolant valve. On May 29th, they tried again, but during tanking, excessive hydrogen was measured in the aft compartment, so they had to scrub. On June 6th, a tanking test was performed to see if the hydrogen leak reappeared, and indeed it did. The thought was that excess hydrogen was leaking from the umbilical connection between the orbiter and the external tank, and then being sucked into the aft compartment. This could not be fixed on the pad, so on June 13th, Columbia was rolled back to the VAB, demated from the stack, and moved to an orbiter processor facility. While Columbia was in the OPF, Atlantis was rolled out to Pad A for STS-38. That also encountered a hydrogen leak problem, though not as severe. After several tests, Atlantis was rolled back on August 9th, where it too was demated and moved off to an OPF. Meanwhile, Columbia was getting some work done. The liquid hydrogen umbilicals were removed from both Columbia and the external tank for inspection. Suspecting the problem was in this area, the same umbilical was removed from Space Shuttle Endeavour, still being built, and was installed in Columbia. With the suspected source of the problem solved, Columbia rolled back out to Pad A on the same day that Atlantis left Pad A for the VAB. The two vehicles actually passed each other in between the VAB and the launch pad, leading to a pretty interesting photo opportunity. Atlantis turned out to have a different problem than Columbia causing the hydrogen leak, and required only a relatively simple swap of components. But a fair amount of time was lost due to the not entirely unreasonable assumption that there was some commonality between the problems. But anyway, we're focusing on Columbia. After arriving at Pad A, STS-35 was rescheduled for September 1st. But there was a problem with the payload telemetry, so it was scrubbed again. On September 6th, they tried again, and scrubbed due to a hydrogen leak in the aft compartment. A crushed seal in main engine 3 was replaced to try to fix the problem. On September 17th, they tried again, and you're not going to believe it, they detected a hydrogen leak in the aft compartment, leading to a scrub. During all of this, STS-41 carrying Ulysses launched from Pad B, clearing the pad. 2 days later, on October 8th, Columbia was moved from Pad A to Pad B, and I believe this is the first time this was done, and I'm not entirely clear why they went to the effort. But there were minor differences between the pads, so it's likely that Pad A had some capability that STS-38 required. Anyway, don't get too used to it, because before they could even finish getting Columbia settled in, the call was made to roll back to the VAB once again due to an impending tropical storm. Okay, we're back in the VAB. I told you this would get a little ridiculous. On October 14th, the ever-patient Columbia was once again moved to Pad B. On October 30th, it underwent a tanking test and did not have a hydrogen leak. After all that, there was no big dramatic culprit, which is kind of to be expected. If the problem was something obvious, they would have figured it out months ago. Instead, it turned out to be a series of relatively smaller things. A nicked seal here, a leaky pipe here, stuff like that. It just took forever to fix because they didn't realize that the hydrogen was coming from multiple problems, and because testing with liquid hydrogen is incredibly difficult and dangerous. It just took some time to carefully work through the issue. Not a great look to the outside world, and it probably shouldn't have happened, but in my mind this isn't anything all that crazy. It's just a hairy tech problem that needed to be solved. After one of the longest series of delays of the entire shuttle program, that all brings us to December 2nd, 1990. The countdown finally went smoothly, and the crew was all ready to launch when at the T-9-minute built-in hold, one last wrench was thrown in the works. The launch commit criteria required a minimum cloud ceiling of 8,000 feet, which just means that the clouds can't be too low. Range Safety sent out a helicopter to verify the weather conditions, and after 21 minutes and 1 second of delay, Columbia was given a go. At 1:49 a.m. Eastern Time, OV-102 departed the launch pad for the 10th time. Ascent was uneventful, which I'm sure the crew was grateful for after all of that waiting. It was time to get to work. The 7-person crew was divided into 2 teams, a red team and a blue team. Mission Commander Brand would just sort of drift from team to team based on who needed him. Each team would have one of the Payload Specialists, one of the Mission Specialists, and either the pilot or another Mission Specialist to change the attitude of the orbiter. That caught my eye since I don't think mission specialists have ever flown the orbiter, even just for an attitude change. But maybe Vance Brand chose those shifts to pay extra attention to. I also didn't run that idle thought down, so who knows. So, what are we doing up here? In Columbia's payload bay were 4 telescopes that could only complete their mission above the Earth's atmosphere. Let's meet them. 3 of the telescopes made up the Astro 1 Observatory. All 3 telescopes were mounted to the Instrument Pointing System, which was a mechanism capable of pointing instruments with extreme precision. The orbiter could point pretty accurately, but when you're measuring stuff trillions of miles away, you're working on a whole other level. Even the slight vibrations induced by the movement of the crew had to be accounted for. With IPS and the other specialized equipment on the unpressurized Spacelab pallets, high-quality data could be ensured. First, let's meet the Hopkins Ultraviolet Telescope, or HUT. This would take the ultraviolet light from distant objects like quasars, galaxies, super-hot stars, and matter falling into black holes, and split the light up, creating a spectrogram. By breaking light into its component pieces, scientists are able to infer a lot about what's going on in the universe. The telescope used a 36-inch mirror coated with iridium, weighed about a ton, was about 12 feet long, and was made by Johns Hopkins University. It would get special attention from Sam Durrance since he was one of the co-investigators on the experiment. Next, the Wisconsin Ultraviolet Photopolarimeter Experiment, or WUPPE, which I'm really hoping is pronounced Whoopie. Whoopie, I'm just going to call it that, studied the polarization of ultraviolet light from distant objects. The topic of light polarization is a little outside the scope of this episode, but it's sort of like how the light is aligned. By studying the polarization, you can learn if the light came straight from a source or was bounced around, among other things. This was pretty cutting-edge science, with barely any data on the polarization of ultraviolet light existing before this flight. The overall telescope was 28 inches in diameter, weighed about half a ton, and was also about 12 feet long. As you may have guessed, it was made by the University of Wisconsin-Madison. And last among the ultraviolet trio was the Ultraviolet Imaging Telescope. This would be the first instrument to take high-resolution ultraviolet photographs of something other than the sun. It was made by the Goddard Space Flight Center, and Ron Paris would be paying special attention to it. Rather than transmit data to the ground, the UIT would expose special film, with enough film on board to take 2,000 images. Included in the telescope was a mechanism to move different filters into the light path, allowing scientists to measure different aspects of the light from different targets. I had to laugh when I saw it mentioned that the final images would be scanned into a computer to form images 2048 picture elements on a side. Picture elements. The press kit helpfully points out that these are sometimes called pixels for short. Yep, in 1990, pixels were not yet an everyday term. The UIT was 32 inches in diameter, weighed half a ton, and was the same 12-foot length as the others. Behind the Astro 1 cluster, we find something a little different, the Broadband X-ray Telescope. The BBXRT was actually supposed to fly a little further down the road, but was added so that it could take X-ray images of a recently discovered supernova. I say it's different because rather than being mounted to the IPS and studying ultraviolet light, it had its own 2-axis pointing system and would be studying, you guessed it, X-rays. Studying X-rays can be handy because they only come from extremely high-energy objects. So for example, imagine a big blob full of stars and gas. The stars and gas could be so bright that at lower energy levels it might be hard to see what's actually going on inside the cluster. With X-rays, it'd be sort of like putting on sunglasses and then looking at a light bulb. Suddenly you can actually see what's going on in there. In this case, it's not really like sunglasses since it's a whole other frequency and not just attenuating the light, but hopefully you get the idea. BBXRT would also be a little different because while the Astro 1 payload would be operated by the crew from the flight deck, BBXRT would be operated entirely by folks on the ground. Since it was just sort of doing its own thing without crew involvement, we'll leave it alone and focus on the ultraviolet instruments on Astro 1. As I mentioned, the crew would be operating the Astro 1 payload from the back of the flight deck. From there, they could look out the big windows into the payload bay and see Astro 1 moving around, and they could also use the control panels and displays to control the instruments. Specifically, there were 2 small displays and keyboards that allowed the crew to control the instrument pointing system and the instruments themselves. Video of what the telescopes were looking at was fed into 2 small closed-circuit TV monitors mounted to the side of the aft flight deck. So, if I understand correctly, the crew would punch in the data for their target on the IPS data display, then use a little joystick and the TV monitor to fine-tune the positioning, and then use the second data display to control the instruments. This system worked great, until around 10 hours into the mission, when one of the data displays suddenly shut down and the crew reported a burning odor. You know the one, the distinct aroma of fried electronics. Well, that's a hassle, but at least there's the second data display. Yeah, no. Around 4 hours later, the second display also shut down and the same distinct odor was reported again. The ground tried to bring the first display back to life, but the crew immediately reported that burning smell again, and that was the end of that. The crew could not point or control their instruments. Well, that stinks, and not just from burning electronics. Mission over, right? Nah, this is NASA. It's time to get creative. Over the course of a few frantic hours, a new system was worked out. Folks in Houston would operate the IPS, pointing the instruments. A separate group on the ground operated the instruments themselves, and the crew continued to fine-tune the observations using the onboard video. It wasn't perfect, and they weren't able to complete all the observations that they had planned. But considering how big an equipment failure this is, achieving 70% of the planned observations was pretty impressive, and ultimately made the science mission a success. But that wasn't the only issue that the crew had to contend with. As the mission progressed, the flow rate of the wastewater dump system started to decline until essentially stopping. The line was clogged. The crew tried pumping some pressurized air down the line, but it didn't help. They didn't know it at the time, but a filter in the line had come apart, creating debris and clogging everything up. Just like with the data display problem, it was time to get creative. But this time it was way grosser. First, the crew bought themselves some time by siphoning some of the wastewater fluid into bags that could be stored in the orbiter. Yuck. Also, I'm impressed that this was even physically possible. If I was on the team designing the wastewater tank, I probably would not have said that there needed to be a way to dump it into the crew cabin. But shows what I know, I guess. That helped for a few days, but eventually the wastewater tank was full again. And I guess they were out of the contingency bags because what they did next was offload the fluid into over a dozen urine absorption devices. So to put that into English, I think they had a tube with wastewater coming out of it that they just pressed into a diaper to absorb. I'm not totally sure because, as you might imagine, the mission report doesn't go into a ton of detail, but in any case, yuck! Oh, and just because at this point I like to pick on tags, I've also got to mention that tags malfunctioned once again by jamming. At this point, engineers were starting to anticipate this. Not only were there defined procedures for fixing the troublesome printer, the STS-35 crew even carried a tool dedicated to the task. So when the text and graphics system once again jammed in the microgravity environment, the crew was on it. They retrieved the unjamming tool, rooted around inside tags, and the tool broke. Sigh. Back to the teleprinter again. All of this makes STS-35 sound like kind of a mess, which it really wasn't. I actually tend to get frustrated when news stories focus on what's bad in the world to the exclusion of everything else. But I like to think that I focus on stuff that went bad, and then the creative solution to get around it. It's the fixing that's interesting. So just because I like to focus on the problems in these missions doesn't mean I think they're doing a bad job. It's tough. Anyway, in addition to a bunch of groundbreaking science, there were also some pretty cool secondary activities. Flying once again was the Shuttle Amateur Radio Experiment, or SAREX. Ron Paris was a licensed radio operator and spent some of his precious free time talking to students and ham radio operators all around the world. As someone who's recently started getting into the ultra-nerdy hobby of downlinking imagery from weather satellites using software-defined radio, the thought of being able to talk to someone in orbit is pretty awesome. Maybe someday. As I mentioned in the outro last episode, this flight features the first necktie in space. As part of NASA's continuing mission of educating students about spaceflight and its benefits, a series of on-orbit lessons were downlinked live all over the world. 4 of the crew members had teaching stints at universities in the past, so they figured that this was a natural fit. I guess slipping into his professorial routine, mission specialist Jeff Hoffman appeared with a dress shirt and necktie. The tie didn't really look like it wanted to stay put, and I can't say that I'm surprised. The mission was supposed to be about 10 days long, but weather was looking pretty iffy in the days to come, with no end in sight, so the decision was made to bring the crew home a little early. Entry proceeded with no issues, though a ground computer that processed TDRS data went down, resulting in an old-school re-entry blackout for 16 minutes. Retro. After 8 days, 23 hours, 5 minutes, and 8 seconds, Columbia touched down at Edwards Air Force Base. The mission had returned a wealth of unique data that could only be obtained in space. And as it so often does, NASA had once again reshaped our understanding of the universe. Next time. Ultraviolet light is pretty high energy, but apparently it's not high energy enough. On STS-35, Atlantis is back on the launch pad and will deploy the second of the Great Observatories, an instrument designed to study extremely high energy light, the Compton Gamma Ray Observatory. Ad Astra. Catch you on the next pass.